Bob Manning is a systems engineer for British Rail.
Signalling systems are broken down broadly into two parts: the safety side of systems and the indication and control. On the safety side, most people are familiar with the mechanical type of lever frame with the interlocking that was provided there. From there we move forward to relay-based interlockings and now into the modern computer-based solid-state interlocking. On the indication and control side of things, the original mechanical box had a simple mimic display. This was superseded by a panel with push-button controls, and in recent years by a VDU display system for the signalman.
The separation of safety interlocking from the other parts of the signalling system is vital to a railway which carries millions of people every day. Later in the programme, we'll look at the way computers are being introduced into the safety systems. But first, we'll see how they can help the signalman carry out his day-to-day duties. The display system in the signal box here at Leicester is run by computer. On the wall, there's a diagram of the track layout for the area covered by the signal box. Around 60 miles of main line between Bedford and Loughborough. There are lamps on the display to represent signals. Each signal has a number for identification, and the numbers are shown on the signals themselves. This signal, number 416, is at the end of platform 3. Back on the display, the track itself can be illuminated to show if a route has been set. For the signalman, a route is just a section of track from one signal to the next. Setting a route involves checking that the track between the two signals is clear. If it is, then the signal at the entrance to the route can be changed, so that a train can move forward. If the track plan on the display shows red, that means there's an obstruction on the track. Possibly a train is present. That information comes from an electrical monitoring system called a track circuit. This can detect whenever a metal object touches both rails of the track. Trains have metal wheels and axles, so if even a single coach is on the track, the circuit is completed and an indication sent to the signal box. To operate the signalling system, the signalman has another copy of the track layout on his desk, with a push button for each signal. Setting a route involves pressing buttons for successive signals down the line. The system then changes the points and signals appropriately. To see the system in action, we'll go down to the station, where the 1525 to London is waiting at platform 4, ready to depart. In the signal box, this train is known by a train code. It's the 1C65. Class 1 trains are mainline passenger trains. The signal at the end of the platform is number 418. So that's the button the signalman will have to press. The next signal is number 404. Pressing these two buttons sets the route between the two signals. Signal 418 turns green, and the route to signal 404 lights up. And by pressing a sequence of buttons, a succession of routes can be set up. Meanwhile, down on the platform, the train gets ready to depart. As the track circuit detects the train's new position, it's shown in red on the display. And of course the signal changes from green to red as the train goes past. Now, to provide these displays for the signalman and to process the information from the push buttons, the computer system needs to contain a representation of the track layout being controlled. Although the track layout may be quite complicated, the data structure used here is fairly simple. It just has to list the allowable routes. The first part of the data structure is like a sequence of records. It's a list of all the different signals which can be used for the entry to a route. The record for each entry signal refers to another sequence, showing the possible exit signals and the corresponding route number. We can see how this works by looking at what happens when a route is selected. Suppose the signalman presses button 409 for a train coming into the station. There are 4 platforms in the station, together with a siding. So there are 5 possible exits for the route. If the signalman presses button 419, the computer will search the list of allowable exits until it finds number 419. That will give the route number. If a train comes on the other track, the entry signal will be 407. This time, there are only 2 possible exits. It isn't possible to get to platform 3 or 4 from here. So if button 419 is pressed by mistake, it won't be found in the exit list. If this happens, the system just ignores the route. The signalman will have to enter it again. But checking for a valid route is only part of the problem. Let's go a little further out from the station, to signal 397. This is the first signal on the station approach, which is seen by the northbound trains from London. After passing it, through trains would go straight on. But this terminating train crosses over to the right-hand track. That's the track normally used by southbound trains. The reason is that this terminating train is due at platform 4. And that's on the right-hand side of the station. So, while this manoeuvre is taking place, the southbound line is blocked. And it remains blocked until the terminating train is safely in its platform and the points can be changed back. So a vital task for the signalling system is to handle conflicting routes. If one route is set, the system mustn't permit another route which interferes with it. Bob Manning.
The safety side of a signalling system is basically termed the interlocking. This is because it interlocks the points and signals to prevent any incorrect movements taking place. On the early type of mechanical interlocking, this was achieved by mechanical mechanisms within the lever frame itself, later supplemented by electrical controls to control the overall system. As we've moved to the relay-based type interlockings, the physical interlocking is achieved totally by electrical circuitry. We're now moving towards the solid-state interlocking, which we're now installing. This achieves the interlocking function by means of safety-critical software within a safety-critically designed system.
In the signal box at Leicester, electromechanical relays are used for the interlocking. There's a large room at the bottom of the signal box containing thousands of these relays, one for each component of a signal or a set of points. You could think of them as forming a kind of computer. The technology is slightly old-fashioned, but that means it's been tried and tested, vital where safety is concerned. Whenever a signalman selects a route, the corresponding relays click into action. They're wired up so that they can only set the route and turn the signal to green if it's safe to do so, if no conflicting routes have been set up. For instance, take the southern approach to Leicester Station. The northbound route to platform 4 is this one, 397, 409, 419. The southbound route from platform 3 is this one, 416, 404. Each of these is a valid route, but they interfere with each other. So if one of these routes has been set up, the interlocking must make sure that the other one isn't allowed. Although much of the interlocking on British Rail is based on electromechanical systems, computer-based interlocking is also being introduced. The Railway Technical Centre at Derby, just a few miles down the line from Leicester, is where much of British Rail's research and development work is carried out. In the labs here, they can put the interlocking through exhaustive tests before it's installed on site, so that they can be sure it satisfies their rigorous safety requirements. The screens here give a display of the track layout, showing points, signals, and track circuit sensors. This layout is for part of the main line near a station. There's a cursor on the screen, and the engineer can set points and track circuits to particular states, and then see what happens when routes are set. This is part of the formal testing procedure, and so it has to be carried out rigorously. To make certain of this, the engineer has a list of the different tests which have to be carried out. The list is prepared to check all possible states of the system, so that there can be no surprises when it's installed. Here, the engineer is setting a route which starts at signal 36. When the route is set, the signal turns green. If the engineer changes the track circuit to show that this line is occupied, then the signal turns red. The software which controls the interlocking contains a large number of conditions, one for each possible route. Here's the condition for the route from signal 36 to signal 34. 3 track circuits have to be clear: T21, T26, and T27. In addition, 2 sets of points, 211 and 212, must be available to be set normal. For these points, that's straight ahead. If all these conditions hold, then the actions can be carried out. Points 211 and 212 must be set normal and locked there. and then signal 36 can be set clear. Once this route is set, the other route from signal 112 to signal 34 will be locked out. That's because one of the conditions for this route is that the points 211, the crossover, are available to be set reversed. And this condition can't be satisfied because those points are locked in the normal position. So this route can't be set at the moment. As the use of computers becomes more widespread, the railways plan to give VDUs to their signalmen to replace the wall displays. In the signal box at Leicester, there are VDUs as well as the wall display, so that signalmen can learn about the new systems. To ease the changeover, the graphics display is made to resemble the wall panel as closely as possible. The track is shown in grey, with routes set in yellow and occupied track in red. But with the use of computers, there are other facilities which can be included.
Calling at Melton, Mowbray, Oakham, Stamford, Peterborough, Whittlesea, March...
These days, the passenger timetable is stored in a computer. The computer can give information about each train calling at Leicester, such as its departure time and the stations where it will stop. One use is for the station announcer, who sits at the back of the signal box. At present, this computer is separate from the signalling system, but both systems use the same train codes to identify the trains. So an obvious next step is to link the two systems together and let the timetable information tell the signalling system where the trains are supposed to go.
We're now moving towards IECC, which stands for Integrated Electronic Control Centre. This brings together a whole area of signalling to be controlled from one point. It can control solid-state interlockings or relay-based systems or a whole combination of either. The information is presented to the signalman by means of a workstation, which has a number of VDUs showing the track layouts, etc. Because it's based on a local area network, we can add on management information systems and ARS, which stands for automatic route setting. This will set routes in front of the trains by means of a timetable processor. We're due to install a number of these systems over the next few years, the first of which comes into operation early next year.
This is the console which will be used to operate the first integrated control centre. At present, it's being tested. But by the time you see this programme, it'll be controlling all the train movements in the vicinity of Liverpool Street, one of the large terminal stations in London. There are 4 screens, which can be switched to show different parts of the track layout, or to magnify any part, or to display a list of messages about the system. Although there is a keyboard, most operations will be carried out with a tracker ball, which moves a cursor across the screen. Just as with the push-button system, the signalman can set a route by moving the cursor to 2 successive signals. This route allows a train to move across to another track. But that's information which has been entered manually. Automatic route setting allows the same information to be entered from the computerized timetable. For instance, the system knows which platforms at Liverpool Street have trains waiting. That comes from the track circuit information. The timetable can then be used to indicate when a train is about to depart. And if necessary, it can set the route out of the station automatically. It can do the same for a train coming into the station. This relieves the signalman of much of his routine work, leaving him free to concentrate on the areas where his special attention is needed. So the steady introduction of computer systems is helping British Rail to increase its operational efficiency. With these additional aids to the signalman, the track can be used more intensively, providing a better service for the passenger. But at the same time, careful design and testing procedures ensure that throughout these advances, the railways continue to maintain a very high standard of safety, the most important service of all.